Hello, everyone. So we have another MATHCOUNTS problem. So this was a national team round question, number 9. So which is a nice geometry problem. So let's get started. So it's a triangle. Point is on segment AC. We are given some ratios. Okay, let's get started with some drawing because otherwise it's not going to help us. So we don't really know the type of the triangle. We just have some ratios. So I'm going to assume it's something like this. If I need to do kind of redrawing, so I will do that. But let's say this is A, B, and C. And there is a point D on segment AC such that AD divided by DC is 2 to 1. So which means AD is longer. So let's say this is point D. And this is, let's say, 2x. And this is 1x. Okay, and then point E on segment AB such that AE divided by EB is 2 to 3. So AE should be a smaller one. So let's assume this is E, and this is 2K and 3K. Okay, and we are, okay, segments AC. E is right here, C is right here. So let's connect those. And DB are intersecting at point K, which is this intersection. And the ratio of KD divided by BK. Okay, so, okay, it's a quite challenging question. Like, there is like a lot of things going on. We have no numbers, but at the same time, we are not looking for actual number. We are looking for some ratio as well. So whenever you are looking for ratios, maybe it's good to think about like area or the similar triangles approaches, so which I'll try a couple different ways. The first thing I'll try using the area approach, okay? So, but it's not really obvious when I say, let's use the area approach. If you are not familiar with the area approach, you probably need to review some of the other videos I share, but I'm gonna just go ahead and dive into how we can use it. So if I connect A and K, the reason I'm doing this because there is a ratio 2 to 1. So if I connect this to 1, so I can have some idea about area of this triangle and area of this triangle since they have the ratios like 1 to 2 ratios. And also that will make some sort of help on this left side as well, since we have 2 to 3 ratios on the left side as well. Okay, that's something. And what I like to do is just finding some relation, right? But I just do need to remind probably something else. So let me go ahead and write in some ratios. So if I want to take the area of the AEK, so this area divided by KEB, this ratio is equal to 2 over 3. Okay, I hope that is for sure clear. Maybe I should write this 2 over 3 on this side. So the reason why that's the case is just because this triangle and this triangle share common vertex K. And if you were to drop the altitude from K to AB, that altitude will be same for both triangles. They have the same height, and the base ratio will be their area ratio. And if I use that same idea with the triangle AEC, okay, and ECB, that is also 2 over 3. Because, again, in this triangle AEC, like AEC, and EBC, they share the common vertex C. So if I drop the altitude from C to AB, that is going to be same for both of these two triangles. And the base ratio is 2 to 3, so that should be equal to area ratio as well. Why do I need this? Because I will use this to get something else. So like, I'm not sure if you remember from the ratio proportionality, like in algebra. So like if you have A over B equals C over D, let's say only two things, you can have more, that is equal to something, okay? And when two fractions are equal to each other, and if this is equal to another number, then you actually can take the difference between these two fractions or sum of these two fractions, or even multiply these by some common numbers and subtract or add with other fraction, then the ratio will not change. So what I mean by that, if you subtract C from A, C, and then B from like D from B, so B minus D, this is equal to K. And if you are wondering why this is the case, I will leave that for you to challenge yourself to see if you can prove it. But this is something we should remember. And based on this, you know, this AEC is the larger triangle, and AEK is the smaller triangle right here. If I take the like difference between this and this, let's see how this is going to look like. The area of the AEC minus AE like K divided by area of this triangle, which is ECB, minus area of the KEB. So this difference, like I just took the difference between these two numerator and denominator, so that should be still 2/3. But at the same time, the reason I did this because I like to see something going on. So if I take this triangle from the AEC, I will get the area of the AKC. Okay, so that's the same as area of the A, K, and C. This is over. Then if you take this triangle from the BEC, you will get KBC. So this is the same as that area. So B, like K and C. Again, if this is too complicated already, then I will ask you to kind of like slowly digest each step. And if you kind of didn't do anything area and base ratio before, so maybe you should better take a look at those for sure. But this is what we have so far. So that's what we have. So the area of this region to this region is also 2/3. So I hope that is clear. So now we are going to use the ratios and give some numbers for those areas. Like if I want to say like this maybe region is like 1A, that means this region has to be 2A because of the bases are the 1 to 2 ratios. And the area of the AKC is 3A. Based on this, I just see that when you divide area of AKC by BKC, that should be same as 2 to 3 as well, which we just proved right there. And since this is 3A, divide by 2, 1.5, which I don't like to deal with that. So I will multiply these by 2 to make it the nice whole numbers. So if this is 4A, this is 2A, the total is 6A. So 6A corresponds to 2, which is 3 times. If you multiply it by 3, so you will get 9A. So this region will be 9A. Okay, so now we are, I guess, good. And after we got this part, then we are done with the problem. Why is that? Because if you look at the triangle BCD, like this one, so we have area of 2A for this triangle, area of 9A for this triangle. So that is the same as the ratio of their bases, like BK and KD. Ratio of this side to this side is equal to area of this divided by area of this, because those two triangles share the common vertex C. So the answer is just 2/9. So this is the first approach, which is not too challenging, to be honest, especially if you are on national level on like team run number 9. So that's way simple, to be honest. But I highly recommend you to look at the area relation between the same base. So that's basically what we use in this case. And then this is some algebraic background. That's the first approach. The second approach I like to use is the similar triangle. So let's try kind of using that as well. So let me pull these a bit backward. Okay, I think I'll take this as well. So I'm gonna keep these for now, but for the second approach, maybe I should clean these as well. Is using similarity. How do I know similarity is useful? Because whenever you have things that is similar, then you can write the ratios easily, which what we are looking is the ratio. But the question that you have to ask, how do I make some similar triangles? Do I have any similar triangles? If there is no, like I need to make something. But the key point is this one. So this is the ratio we are looking for. So if you are looking for this guy, so you just need to make something that will help to get this ratio. So what I'm gonna try, since we have 2 to 3 ratios, maybe we should use them. So otherwise it's not gonna be helpful. So what I'm gonna try, I'm gonna draw a line from E to AC in a way that will be parallel to BD. So let's say this is parallel to BD. Why this is important? Because if I draw this line, I do know the ratio of this to them. That will give me the ratio of this to this as well. So let's say this is like T. And then if I do have some ratios, then the rest will be easier to deal with. So like, since this is 2 to 3, then if I call this is like 2, I don't know, like Y, and then this is gonna be 3Y as well. So that is something. But we already know from the D to A was 2 times X and DC was 1X, which means AD was twice of DC. So we already know now AD as 5Y. So that means this is going to be 2.5Y. And if you don't like dealing with decimals, you can just multiply by 2 and then you can just double these numbers as well, which is also okay. We got this as 2.5Y, and then this is 3Y, this is 2Y. And also, since BD is parallel to like ET, then we do have DKC is parallel to TEC. And the ratio, like I'm not sure if you are good with the similar triangle, so the ratio is this to this. So that looks like 2.5. I don't care about the Y part because we just need ratio, divided by 3 plus 2.5, which is like 5.5. And if you multiply by 10, that's 25 and 55, so 5 over 11. So meaning that if I call the like this piece KD, because that ratio will be same as KD divided by ET because of they are corresponding sides. So then if I call this is like 5T, so that means this is 11T. Okay, so something useful. And the last thing we have to find is B to K. And I do know AET and ABD is also parallel. So if you don't see it, make sure you kind of take a look at it carefully. So because these two are parallel, so the AET and ABD are similar. And the ratio is, let me use different color. The ratio of that similar triangles is 2 over 5. So that is my ratio, 2 over 5 equals this ET divided by BD. So I will say 11T over BD. And if you do cross multiplication, so you will get 55 over 2 for BD, right? So that's 27.5 T. And this is 5, so if you subtract 5 from that, so you will get 22.5 T. So if I didn't mess anything with my fractions or numbers, I should be getting this same result. Let's check that. So we got 5T over 22.5 T. So multiply by 10, so that will be 50 over 225. I can divide by 25, so that's 2. And this is 9 times 25, which is 9. As you remember, this was our answer, so we are good with that. So this is the second approach using the similar triangles, which I guess wasn't. So the third approach I'm going to try is called math point. So if you never heard this, that is actually good to know because that will be way better in some cases. In those cases, like when you are using the math point, you don't really need actual numbers, so you can just use just the ratio, even though, you know, we don't know if this 2 and this 2 is equal. In the first approach, we should make different variable, but in this approach, we don't really need that either. Okay, so like, what does that look like? So if you never heard the math point, so that is good to do as well, and then I can make more videos if needed, but just let me know. So here's the thing, you know, math point is just using scale in a way in our triangles. So you are just assigning some masses on each vertices, okay? So how that looks like, for example, if I assign a mass right here, like 1, 2, whatever, but I like to multiply the mass right here and by 2, that product is equal to this distance by the mass at B. So which is why when you are assigning masses, you are going to look at the numbers you are given, which is 2 to 3. So you can just choose the opposite of those. So let's say this is the mass, which is 3, and then the mass at point B will be 2. So because 3 times 2 and 2 times 3 will be equal. And the same idea, 3 times this distance, which is 3 times 3 is 6, and then 1 times the mass right here should be same. So that's why the mass at C is going to be 6. So now, as soon as you have the masses on each corner, you add this mass by this mass, which is just 9. Okay, but 9 is the mass at the point D, and then the distance between A to C was the 2 to 1, right? And you can just, like, we just use that to get the 6 first, and then we just add this mass and this mass to get this middle mass. Okay, if I want to add the, like, if I want to find the mass right here, which is 3 times 3 plus 2, which is 5, which we don't really need to find this one for the sake of this problem, but if you need to, you can get as well. But now our goal was this ratio, so KD divided by BK. So I said if you take this middle point of D and B, the mass right here is 9, the mass right here is 2. So when you multiply this mass by this distance and this mass by this distance, you should get the same results. Only way that will happen if this is 9 times something, and then this is 2 times something, and then we got 2/9 ratio without really doing a lot of work. So you can do this question probably less than 30 seconds if you have some experience with the mass point, and that's basically what we have. And if I really want the ratio of E to K, K to C, then you have 5 to 6, right? Which wasn't asking the problem, but let's try that as well for the sake of practice. So since this is 5, this is 6, then if I say KC to be like 5K, then EK will be 6K, and that's gonna be ratios. So the math point is really nice when you are finding ratios. So if you have some ratio question, you usually go with similar triangles, finding some similarities, which is okay. In some cases, you can use the area approach, but math point is way better in most cases. But I don't just rely on the math points, but it is really helpful in some occasions, okay? I hope that's clear. I'll see you in the next video.